Alright, y'all, my name is Alejandro Miranda. This is essentially the questions I gotta do for physics. Sorry for it being a bit late and the strange setup I find myself in, but hey, again, it's the only kind of quiet place I can find. Hopefully y'all can hear me right. The AC is going a little but who knows? The whole point is that as long as you understand these questions, what's going on, and the fact that I understand these questions perhaps can help us out in the future for our IB exam and whatnot. So essentially the questions I had to do were obviously for astrophysics because I ain't no scrub, are 6, 16, 4, 14, and 2, and 12. We'll go over all of them in each part. Do not worry about essentially reading what's on the paper, because essentially I will try to explain everything in the most detail that I can, and something that's understandable to me. So hopefully this helps y'all out. And if I have to reference like parts in the textbook or stuff on the booklet, got the booklet, I'm not pulling out the textbook, so you're just gonna have to deal with it. And hopefully this really helps y'all out, because I mean, this is kind of a pain, but oh well, let's get this done. Alright, so our first question is 6A. Describe one key characteristic of a nebula. So essentially this is one of the easiest questions that is on the test. It's essentially like, what is a planet? Describe a planet. What is a star? What does a star do? Etc. So essentially, if y'all don't know what a nebula is, just some basic information, is essentially just a cloud of gas and dust that essentially roams around the universe and is essentially the foundation of most stars. Because obviously due to gravity, particles clump together and form larger things, and that's the best way to explain it. God, I'm terrible at this, but oh well, what can be done? Essentially, due to gravity, things come together and they grow bigger and bigger and bigger. And as things grow bigger, they have more gravity and whatnot. And so essentially, that's what a nebula is. All this gas and dust clumps together, keeps growing bigger and bigger and bigger, until the point that is able to start and commence doing nuclear fusion, which is what defines a star. We went a little off track, but alright, so essentially, to answer the question, all you really need to define is that it is a cloud of gas and dust that is attracted enough by gravity that it doesn't fall apart, it doesn't just separate itself, but it doesn't fuse together as gravity generally does. Essentially, it's in a state of balance, and unless an external force hits it, the clouds of gas and dust won't come together to make, as what you know, stars and whatnots. And so essentially, that's the one thing you really need. And essentially, just to keep it simple, really simple, it's just a balance of attraction of gravity. It's the force of gravity is not too strong, it's not too weak, it's just right. It's just enough so that it has to take something else in order to, actually form a star. Now, alright, so the AC is turned on. Apologies, I was trying speaking as loud as possible because I can't hear because I'm outside, but alright. And the next one is Beta Centauri is a star in the southern skies with a parallax angle of 8.32 to the 10th times 10 to the negative 3 power arc seconds, calculating meters the distance of the star from Earth. Alright, now this is surprisingly easy, but it's a lot of conversions. Thank God it's in the book, and thank God it's in the booklet, I believe. And as you see here, I did the calculations. So right off the bat, you're trying to find meters. And in order to find meters, you got to go from arc seconds into parsecs, which is a way of measuring distance in astronomical terms. So it's 1 over the given value. That gets you 120.19 parsecs. Now, from parsecs, you have to convert it into light years. 1 parsec is 3.26 light years, which is given in the booklet, so you don't really have to remember that. Just look for it and you'll be alright. So do the math once again, and that gets you 391.82 light years. So we still got to do even more math, because 1 light year is equivalent to, as you see here, 9.46 times 10 to the 15th power. That's a big number. Apologies for the blur. But I'll keep talking, hopefully it'll focus in. But anyway, multiply it out once again, and the value you'd get is a total of 3.71 times 10 to the 18th power meters. That is your answer. If this is wrong, oh well, but this is the way to do it. It's just a conversion, once again, from arcsec to parsecs to light years to meters, and you're done. And now, the final part of this question, which is really the easiest one. Hopefully I'm right on this part. Might not, because I think I did a little too simple. But essentially, the question is asking outline why physicists use non-SI units for the measurement of astronomical units. SI meaning, you know, your meters, your grams, and whatnot. The answer is quite simple, and it's straight up given in the book in the first chapter regarding astrophysics. Essentially, SI units are just far too small and just far too inaccurate to really accurately depict the universe, since the scales we're dealing with are, pardon my pun, astronomical in nature. So it's imperative that scientists use larger units in order to get a better picture and just make their lives and calculations just a whole lot easier. That's really all it is. And with that, we got 6 done. Alright, let's move on. Once again, forgive me for the terrible audio quality. Nothing really I can do about that, but oh well. Hold on, let me take a sip. Alright. Next question. 16A and 16B. We'll start with A. Essentially, you're trying to find luminosity. Luminosity is given in the physics textbook, physics booklet, and only this once will I actually look for it. Let's try to find it. Alright, here it is. In order to find luminosity, there is your equation right there. Good job. It's really not that hard. L is for luminosity. This little thing, which I really don't know what it's called, but it is a constant and it is given under the list of constants. So just look for that symbol and it should be there. A will be replaced, as you'll see later as I explain, and T is obviously temperature to the fourth. God, I'm terrible at this. Oh, alright, continuing. Moving on. Essentially, they tell you that the temperature of star A and the temperature of star B is TA TB, and when TA is over TB, it is equal to 0.6. Radius is the same situation. Star A is RA, star B is RB. RA over RB is 270. Alright, we good. Okay, so essentially all you really have to do is to apply the formula that is given in the physics textbook. And instead of using the value of A, you replace it with, if you have a focus, I'll just say it, 4 pi times radius squared. Finally focused. Okay, cool. And essentially, you keep the temperature because that's just a part. This is just a way to expand the equation, the formula you're using. So essentially, you put this out, you lay this out, and as you know, since what we're trying to find is luminosity, these values, as mentioned here, the constant and 4 pi cancel out completely, which would just get 1, so that doesn't really matter. And so what you're given is what you had before. RA over RB is 270. TA over TB is 0.6, except now we have the powers in play. So you have 0.6 for temperature to the fourth and times 270 squared. So that gets you on your magical calculator, using calculator magic once again, you get 9,447.84. Or if you really want to simplify it, that's really all it is, if you just make it 9,400 point whatever, you get 9.4 times 10 to the third. Alright, easy peasy, surprisingly easy. Essentially, you're just taking the formula you got from your magical booklet, switching the value around just a bit, and just plugging what you got and canceling things that don't really matter. So, easier than I thought. Here we go. Now, the next question is about the diagram below shows the spectrum of the stars as observed from Earth. The spectrum shows one line from star A and one line from star B when the stars are in the position shown in the diagram. On the spectrum, draw lines to show the approximate locations of these spectral lines after the stars have completed 1/4 revolution. So basically, if we're looking from Earth, they say draw one line, and so I would assume that star A is closer. So just from the perspective of Earth, this would appear a lot closer, and then B, since this is further away, it would be a little further. I'm not really too sure about this. Still kind of fuzzy on this, and the book doesn't cover it too much, so forgive me on that part, but that is the answer, and do with it as you will. Hopefully we'll get to learn a little more, study a bit, and alright. But on that note, we've got to move on just a bit, and that brings us to question 4, to the wonderful world of cosmology, because now we're going to start talking about cosmic microwave. Hold on, am I right? Am I saying? Oh yeah, okay. Cosmic microwave background. I forgot radiation, and it says radiation right there. My bad. I'm telling you, man, this is impromptu. All right. So it says state 2 characteristic of the cosmic background radiation, and I put 3, just just to make sure. All right. So one, all you really need is 2. I guess you can ignore the 3, but that can be applied a bit later on in the question. So we're just gonna stick with these first 2. First of all, it has currently a temperature of 2.73 Kelvin. All right, this is stated in the book, and this is apparently something key to understanding CMB radiation, because it is just given, and in certain occasions, as you'll see later, you're kind of gonna need to apply this fact, unless actually they give you the temperature. But it's also good to know. And one very important thing, and actually this relates to generally like the origin of the universe and the Big Bang, is that it is a uniform wavelength of 1 millimeter. Hold on, just a minute. Just let me make sure I'm saying it right. Don't want to screw y'all over. Millimeter. Yeah, my bad. All right, millimeter. 1 millimeter in all directions. Since the universe is so vast, this radiation essentially is, I forgot the term they used, but it's just constant in all direction. It's always 1 millimeter and always has been for a while, as of now. All right, that's really all you need. Just write that down. Boom, boom. That's 2 marks. You did it. Cool. All right. So now the next question for B is the present temperature of the CB. Cosmic microwave background radiation is 2.8 Kelvin. Calculate the peak wavelength of the CMB. This is Wien's law. I don't have the book on me because PDF for the win. This is Wien's law. It is on page 440. So if you want to look it up, it is literally exactly this, which it doesn't want to focus, so it's okay. So essentially, your equation is 2.9 times 10 to the negative third over temperature. We obviously have given this, and we have given temperature. So do the math, and you get 1 millimeter. Ta-da! 1 mark. What did you expect? Let me take a sip real quick. Hold on. Sorry about this. All right. Next question. Describe how the cosmic microwave background radiation provides evidence for the hot Big Bang model of the universe. Didn't know there was a cold Big Bang model of the universe, but oh well. Alright, so essentially, first of all, you have to understand what the Big Bang is. This evidence is right off given in the chapter that covers this. It's like the last part. It's cosmology. So as long as you read that, you should be fine. And essentially the whole thing is that prior to the Big Bang, the universe was of mostly black body, I can't zoom in, of black body radiation, which is essentially all forms of light are just absorbed. There's no light in the universe. There's just nothing. It's just dark. Until, of course, the Big Bang happens, and light comes out. And obviously, this dispersion, reading my answer. This dispersion of the black body radiation essentially allows for what becomes the birth of our universe after the Big Bang. And scientists theorize that the cosmic microwave background radiation is just leftovers. It's just, essentially the bones of what was once black body radiation. Alright, just keep that in mind. CMB essentially just says that black body radiation existed because I'm still here. Alright? Cool. Yeah. Horrible quality, I know. Alright. Okay. Alright, next question. Alright, this is important. Yada yada, spectral line, boo boo boo. All we need to know is a redshift. Z equals 0.16. Alright, good. Cool. Okay, determine the distance to this galaxy using a value for the Hubble constant. It's in the book as well. Of h equals 68. Yeah, you know. Kilometers per second, megaparsecs. Parsecs are very important. Essentially, to find z, you would need obviously z, which is the value given, velocity, and c, which is the constant for the speed of light, which, haha, surprisingly, is also given in the book, in the booklet. So you really don't need to know that. Essentially, plug in your values. You have z. You're trying to find v. You already know the constant of c. I'm really sorry. It's just this camera's really not working out for me. You plug in your values. You get 0.48 times 10 to the 5th kilometers per second. Now that you have the velocity, we have to find the distance, which is just velocity over the Hubble constant. And well, what you know, we have the Hubble constant at our disposal, and we also have the my bad, I'm blanking. Okay, we have the velocity. Plug that stuff in. Velocity divided by the Hubble constant. Sorry, but I'm trying to explain it the best I can, but this camera's still not working with me. And that'll get you a total of 706, or if you want to round it off, because for whatever reason, you get 710 megaparsecs. Alright? That is your answer. Good job. That is like 2 marks, so there you go. Alright? Next one. This is actually a lot easier. Estimate the size of the universe relative to its present size when the light was emitted by the galaxy in C, which obviously is referring to the previous answer you got. Alright, cool. Alright. Now, once again, we're going to apply Z. And Z is known to be equal. Actually, it's not this way. Oh, if I had my pen on me, which I apparently lost. What it is essentially is that normally R over R0 is R0 essentially being the factor, the initial factor, which would always be 1. R over R0 is equal to Z plus 1. But, you know, they transferred it, so just better V's. Because we have Z. Now we just gotta solve for whatever this is. So we already have Z, because Z is previously given. And so it's 0.16. And so we add 1.16. And so essentially all we have to do the reciprocal, since essentially the original R value, whoops, I didn't do that part, forgot about that. But essentially R0 goes on top because that's initial, it is 1 divided by 116, which is essentially just 100%. This is the current size of the the universe. And so essentially 1 divided by 1.16, that gets you 0.86, or in reality 86% of the present size. Alright, pretty good. Okay, hopefully y'all are catching on. The audio is not too bad, because this is not getting edited. This is completely impromptu. Alright, next question, 14. Now this is really easy. If you take an L on this one, I don't know what to say. I'm not that good at physics, but like, come on. Alright, this question is about the life history of stars. Outline with reference to pressure how a star on the main sequence maintains its stability. Now, if you don't know, stars are essentially like living beings, except not being living beings, because they use nuclear fusion to survive, and we do not use no living being that we know of uses nuclear fusion to survive. So essentially, there are something called sequences, like from the birth, and what we're going to focus on is main sequence. And essentially, it asks, outline with reference to pressure how a star on the main sequence maintains its stability. So this is really basic. You don't even really need to know physics for this part. Essentially, all you gotta understand is that stars are incredibly huge and have an incredible mass. It's astronomical mass, if you really want to say that. And this mass obviously causes an increase in gravity. Gravity is always pushing down on it, and essentially, the star is always being crushed on and pushed by, pressure of gravity. But in order to maintain its size and, you know, maintain its existence, what it does is that at a certain point, main sequence stars survive based on the nuclear fusion of hydrogen into helium, which releases an enormous amount of energy. Enormous. Well, not really, but a big amount of energy. This is the energy that the star uses to create a counter pressure, in a sense, against gravity. So essentially, this balance of pressure allows the star to maintain its stability. And during the state, as long as it has fuel to burn, fuel being hydrogen, it will maintain its stability by pushing back against gravity against its own gravity. All right, that's really all you need to say about that. So let's move on. All right, next one. All right, last two questions. Oof. Let me take a sip. I'm terribly sorry if this comes out weak, but I have to, gotta work with what I got. So, alright. Next question. Look at this graph. Number 2. Estimate using the data the age of the universe. Give your answer in seconds. So, actually, I believe I got this wrong. I think so. But I believe the process is right. And that's really all that matters. Alright. So, essentially, in order to find out the age of the universe, you have to do the distance over the recession velocity. This is also in the book. It's given in the book. But I just at this moment, I don't really remember it, and I'm using my phone to record. So really bear with me. So essentially all you need to know is that it is distance over velocity, because we are essentially applying the fact that the Hubble's law is essentially what forms it. Which, if I can find Hubble's law, which I'm sure will go later. But essentially, that the further away that galaxies are from us, the faster away they're going away from us. That's just basic. But alright, that's enough. Okay, let's focus on the question again. Kind of lost track. So essentially, they're asking you to find it in seconds. In order to find it in seconds, you got to do kilometers per second, which is obviously given. So instead, I chose for the point A because that was just the easiest to do. 4.6. So in order to get proper kilometers per second, because I just despise scientific notations, I essentially just did the calculator, used the calculator, and got 46,000 kilometers per second. That's cool. Then I got my velocity now. And now here comes the fun part, where you have to convert megaparsecs, not just parsecs, megaparsecs into kilometers, actually. Boy, am I dumb. Yeah, kilometers. So essentially, if you remember what we did back for one of the previous questions, it's just a lot of conversion. First, you gotta go from megaparsecs to regular parsecs, which luckily the booklet has the representations of mega, and mega is just an equivalent to 10 to the 6. So just do that. Value is 560, as I just lined that up. 560 times 10 to the 6 gets you big number. 560 million, big number. Then parsecs to light years, and light years to kilometers, which got me 1.72 times 10 to the 25th. So essentially, I just plugged those values in, divided it, and got 3.75 times 10 to the 20th seconds. I believe this answer is wrong, but the process should be right. And so as long as you get the process right, as long as you know how to do your equations, as long as you know how to apply the formula, you should get at least a couple marks. That's really what we're trying for. You're not trying to take that big of an L. You're trying to make it. So, alright. On that note, identify the assumption that you made in your answer to A. Now, this is actually pretty interesting, because generally when you're dealing with the age of the universe, with these kind of values, we're overestimating. Because we're assuming that velocity, the assumption made is that velocity is constant throughout. As you know, velocity prior to the present time, is actually slower than it is now. It keeps accelerating for us, so the velocity is not constant. So essentially, you really can't accurately find the age of the universe without doing some wild stuff. And so they'll never really ask you to find accurate. And so that's why they're giving you what assumptions you gotta make to get the answer. So velocity is constant. Always remember that when you're dealing with the age of the universe. Alright, cool. And one last part. Once again, we're applying redshifting, value of z. And once again, we return to V over C, velocity over C, which is a constant if you didn't know that, as previously mentioned, which is the speed of light. Velocity, now you just gotta plug it in. That is literally all you have to do. You gotta find Z, and then you gotta find, once again, the R factor and whatnot. Okay, so Z we don't know, but we know velocity and we know the speed of light, because speed of light is a constant. Speed of light is 3 times 10 to the 8th, and you know the velocity because it's given on the graph. So essentially all you gotta do is 4.6 times 10 to the 4th, which gets you your kilometers per second. But if you want to go a little further, which you kind of have to, you gotta go for meters, which is also times 10 to the 3rd, which is times 1,000. They just want to be like that. And so that gets you 0.15, that is your Z. Now, with your Z value, you add 1, because of course that is just how the equation works, and that gets you 1.15. Now, you do the reciprocal. The present value, it is 1, so 1 over 1.15, that gets you 87% of present size. So all you have to do, once again, is plug it in, knowing your equations, and I believe, if I'm not wrong, boop, that's, yep, there it is. The equation, if it would focus, is right here in your cosmology section, right there. You see it, right there. I can't really point it out. There you go. Alright. Last question. Alright, let's get this right. Now, this question is a lot more theoretical and whatnot. So, here's the question. Theoretical studies indicate that the universe may be open, closed, or flats. Number 1, state by reference to critical density the condition that must be satisfied for the universe to be flats. Alright, so this is also in the book. Boy, oh boy. Actually, I had to find this online on another textbook. Kind of sucks, but what can you do? What can you do? So essentially, in order for the universe to be considered flat, the critical density of the universe must be equal to the actual density of matter in the universe. This is what the textbook said. Alright, that's really all there is to it. So essentially, it doesn't expand out just ridiculously. Like, just to understand, flat is just constant expansion, but just eventual decline into just zero expansion. Open is just infinite expansion. Closed is essentially, if you're not familiar with, you know, theoretical sciences and whatnot, man, I can't really say it. Closed is essentially the big crunch. We will expand, and all of a sudden, it will just, the expansion will stop, and it will just reverse. Alright, just keep in mind, critical density must be equal to the actual density of matter. This is what is said. So as long as you're with that, you should be fine. B, it says that in a flat universe, the rate of expansion would be slowing down. So just a reason for this. Now, in the textbook that I read, which is another IB textbook, it says that open, closed, and flat are essentially theories that revolve around the idea that dark energy does not exist. If you're not familiar with dark energy, it is the theoretical. Alright, we're going into some theoretical stuff. Bear with me. Dark energy is essentially the unknown quantity that scientists have essentially just placed on what is driving the expansion of the universe. Because it can't be gravity, and there's something pulling at the universe that we can't see. So scientists just call it dark energy because, let's be real, nobody really knows what it is so far. Alright, what did I put for this? Okay. So essentially, what I put is that in the assumed absence of dark energy that facilitated expansion, essentially, since there is a balance between densities, although there would be infinite expansion, eventually, then it wouldn't be infinite expansion. Although there would be prolonged expansion, eventually it will hit zero. And so this is due to the lack of some accelerant known as dark energy. Maybe I'm wrong, but that's what I put. Alright. And the last question is, outline why it has been difficult to determine whether the universe is open, closed, or flat. Now, I don't really know what to put for this. I'm gonna be real, but I really reflected back on dark energy, so I may be wrong. Hopefully, I'm not. But let's go on with this. Essentially, I put determining the nature of the universe is difficult with the values that are known to us. Scientists are forced to assume the existence of unknown quantities to determine what the universe is. So essentially, we can never really be sure whether the universe is open, closed, or flat. For one, we barely understand the origin of the universe, we say, but this is all theoretical stuff. There is no there is no evidence that flat out says that this is the way things are supposed to be. As you know, at the very beginning of the universe, we have no idea what happened. The Planck time, they call it. And many of the forces that control our universe are unknown quantities to us. That's why we have things called dark matter and dark energy. Dark energy, especially, is one of the bigger ones, as I said previously, is what's driving the expansion of the universe. We have no idea what is actually driving the expansion of the universe. You have no clue, so we just threw the word dark energy on it, because we have no idea, and for that reason, we can never really be sure what is the nature of the universe, whether be it open, closed, or flat, as given in the question. That's all you need. Went a bit on a tangent there, but all right. Last question. Thank God. Outline one piece of experimental evidence that supports the fact that the universe is expanding. This is incredibly easy. Literally found in the book. It is known as Hubble's law, as I mentioned, and all you gotta do is read it out. As long as you know the definition, there you go. You got 2 marks. Hold up. Recessional velocity of a distant galaxy is directly proportional to its distance. So I didn't put in the book. They give you like a dumbed down explanation. That's a terrible way to put it. But they give you a more simplified explanation. Essentially, that there's a linear relationship between the distance of a galaxy and its velocity, recessional velocity, which is essentially how fast is it going away from us. All right, because due to dark energy, it is assumed that everything, the entire universe, is just spreading apart incredibly fast. So what this is essentially saying is that the further the galaxy is away from us, the faster it is moving away from us. All right. And on that note, that is all my questions. This is a pain. I'm sure a good amount of these I did probably get right, but feel free to check for yourself, because these might be wrong and I did not get a chance to see the mark scheme. So, alright, I don't know how to end this off. Thank you for watching. Sorry for this being too late, and alright, good night, y'all. I'm really tired. Alright.